Okay, here we are. We are looking at remark 211. So we're going to consider we've got a function going from x to y. It's injective. And our claim is that happens, namely f is injective if and only if, so we've got a two-way implication, if and only if, when we take the image of f of A and the image under f of B, we get the same thing as the image under f of A intersect B for all pairs of subsets A and B and X. So let's take a second. First, let's clean up all of that highlighting. Let's take a second to remember what is f of A. So if I've got this function, so recall that if I've got A a subset of X, then what does f of A mean? Because A is a subset, and the function takes elements to elements. So what this notation means is that this is the set of all Y contained in the codomain such that there exists an A sitting inside of my subset A such that f of little a is equal to Y. So if I draw myself a picture, here's X, here's Y, maybe here's my subset A inside of X, then what I'm looking for is all the places that A goes. So this is f of A. These are all of the images of all the points of A. Where do they go in Y? That's f of A. Okay, so what's our claim? We've got a two-way implication. So we have to show, so let's not call it A, let's call it 1. We have to show if f taking x to y is injective, then f of A intersect f of B is equal to f of A intersect B for all A, B subsets of X. And then 2, we have to prove if it's true that for every A, B subset of X, we have f of A intersect f of B equals f of A intersect B, then we have to somehow show that f is injective. Okay, so let's start with 1. So I'm just going to scoot 2 down a little bit out of my way. Oops, that didn't work. So let me scoot 2 out of my way. That was a disaster. One more try. Maybe another try. There we go. Okie dokie. Looks like I took a little bit of injectivity with me. So let's put 2 down here. Okay. Get rid of the J from injective and put it back up here. All right, so right now we're just worrying about if f is injective. If f is injective, then we have to show this set equality. Okay, so we have to remember that to show a set equality is to show 2 things. So let's just get started. So we assume f is injective. And we want to show that f of A, well, for every A, B contained in X, we have 2 things, f of A intersect B, f of B. F of B equals f of A, not equals, is contained in f of a intersect b, and f of a intersect b is contained in f of a intersect f of b. So let's look at our picture again. So what's going on is we've made our picture a little more complicated. So let's blow it up a little bit. I've now got an A and a B. So here's my A, here's my B, and there's my A intersect B. And then they both get mapped over into some, here's f of A, and maybe over here's f of B. And what this is saying is if it's injective, then this little lozenge here is going to get mapped exactly into this little lozenge there. And so that must mean that it doesn't always happen that way, right? Okay. So let's just start trying to prove it. We know that it's injective, but we're going to start with the set inclusions. So I'll call this I and this II. Okay. Well, if, suppose I have a y sitting inside of the image of A, f of A intersect the image of B, f of B, then what does that mean? Well, it's an and statement. Y is in f of A, and y is in f of B. Since it's the image of A, that tells me there exists an A contained in A such that f of A is equal to y, and there exists a B contained in B such that f of B is equal to y. But what that tells me is I've got f of A is equal to y, which is equal to f of B. Now I can start thinking about my hypothesis of injectivity, right? So if f of A is equal to f of B, and I'm injective, what does that tell me? Well, the only way that two values can get mapped to the same value in the codomain, if my function is injective, is if A and B are equal. And if A and B are equal, what does that tell me? It tells me, since A then, as A is contained in A and A equal to B is contained in B, that tells me that A, which is equal to B, is contained in A and in B. All right? And y is equal to f of A, which equals f of B. And so that tells me that y is contained in the image of not only A, but also B. Because little a and little b are equal. All right? So now we've proven part 1. Part I. So now for double I, we start with the opposite inclusion. If y is contained in f of A intersect B, we want to show, what do we want to show? If f of A intersect B is contained in, we want to show that it's contained in f of A intersect f of B, and we're still under the hypothesis that f is injective. So off we go. If we have y contained in A intersect B, what does that tell me? That tells me that there exists an x contained in A intersect B, such that f of x is equal to y. All right. Since x is contained in A and x is contained in B, that tells me that f of x is contained in f of A, because it's the image of something in A, and f of x is contained in the image of B, because x is also in B. And that tells me that f of x is contained in f of A intersect f of b. And notice that in this argument, I did not use, so purple's going to be hideous. Let's use blue. Notice for double I, we did not need f to be injective. Okay, so part 2 always holds, and part 1 is the part that only holds with injectivity. Okay, but we're not done. So what we've done now, this completes the proof of part 1 of our statement. Remember, this is the forward implication. If f of x, f mapping x to y is injective, then we have this set equality. Okay, but we still have the second part, which we wrote down here, which says, if for every a and b in x, we have that the image of the intersection of the image is equal to the image of the intersection, then f is injective. Okay, so that's what we need to do now. So let's start in the beginning. So we assume, proof, we assume that for every a and b in x, we have f of a intersect f of b equals f of a intersect b. And we want to show that it's injective. Well, how does an injectivity proof go? So you remember that injective means that for every y contained in the image of f, there exists a unique x contained in the domain such that f of x equals y, right? All right. So there should be only one x mapping to y. So we could go off and try and prove that directly, or what we can do is pay attention to the fact that we're doing a uniqueness argument. So what we said before is when we say that something's unique, the easiest way to prove it is to suppose there exists x1 and x2 contained in big X such that f of x1 equals f of x2, or equals, let's give ourselves a y, equals y, and so does f of x2. So suppose there's a y that has an x1 and an x2 that maps to it. What we want to do is show, so let's make that remark in blue, we want to show x1 equals x2. That will show injectivity. So let's start doing that. So we've got f of x1 is equal to y is equal to f of x2. So what we're going to have to do is we're going to have to use our hypothesis that whenever we have a and b in x, we have that the image of A intersect the image of B is equal to the image of their intersection. So let's see if we can make a clever choice of A and B. So consider the set A to be just the set containing x1 and the set B to be just the set containing x2. Then what do we have? If we look at A intersect B, that's either going to be the empty set if x1 is not equal to x2, or it's just going to be x1, which is equal to x2, in the case that x1 does equal x2. And since that's the case we want, that's where we want to land, so we need to eliminate this possibility. Okay? So let's see what happens if it is the empty set. So suppose that A intersect B is the empty set. Then what is f of the empty set? So So F of the empty set. So that would be the place where the empty set gets mapped to. Well, there is nothing in the empty set, so it gets mapped to the empty set. Okay? But we know that this is equal to, by our hypothesis, this is equal to f of A intersect f of B. So what that tells me is that if I assume that f of A intersect f of B is the empty set, then I get that f of A intersect f of B is the empty, which is equal to f of A intersect B is equal to the empty set. But remember, what is f of A? It's x1. Sorry, f of x1, what am I saying? It's f of x1 intersect, and this is f of x2, because those are the only elements inside of those sets. But f of x1 is just y, intersect f of x2 is y again, so this is equal to just the set y. And so what we just said is the set with the element y in it is equal to, following all the way around here, following all the way around here, what this tells me is that y is equal to the empty set. And that's a contradiction, because y was an element inside of, right here, y is the image of something that was non-empty, and therefore it can't be empty. Everybody has to get mapped somewhere. So we got a contradiction. Where did we get that contradiction from? Let me shrink it down a little bit, this piece right here. Oops, that wasn't a good idea. Let's first get rid of this little awkward arrow here, and I'll try and shrink this whole part down. Here we go. So where did all of this contradiction come from? It came from our hypothesis we had that A intersect B is the empty set, got me to this contradiction. That means that my assumption must have been false. Thus, A intersect B is not equal to the empty set, and we said that if that's the case, the only possibility is that A intersect B is just equal to x1. Now, what on earth were we trying to prove? We were trying to prove that it's injective. So we were trying to prove that x1 equals x2. Well, if A intersect B is equal to x1, and A is equal to the set x1, and B is equal to the set x2, the only way you can have the intersection of two different sets and get one of the other ones, so the only way we can intersect the set with x1 and the set with x2 and get the set at x1 again is if those two elements are equal. And that shows that it's injective. Okay, so now let's look at the next statement here. So we've got a function again, and we've got a subset of x and a subset of y. And the first statement really only addresses the subset of y. So let's pay attention to that for a second. So if we were to draw a picture, here's our x mapping onto our y, and we've got a set here, B. And now what we're talking about is an element inside of B, and we're going to be looking at the pre-image of B. So this guy here is F inverse of B, and so that's all the stuff that gets mapped onto B. And we're going to look at the pre-image of an element inside of B, and we're going to make the astonishing realization that the pre-image of Y, if we look at it in X, is going to be sitting inside of the pre-image of B. That's not enormously surprising. So let's prove that. So proof of A. If Y is contained in B, and I consider F inverse of y. Well, what is this? This is just the set of all x's such that, sorry, x is where? X is in the domain such that f of x is in the set y, but since the set y only has one element, it's just equal to y. Okay. And then I've got this preimage of b, which is a set. So this is the x's in x such that f of x is an element of b. And what I want to show is that the first set, the preimage of y, is contained in the second set, the preimage of b. Well, if I have a little x sitting inside of the preimage of y, then what do we know? We know that f of x must be equal to y, and since y is sitting inside of b itself, if I just start from f of x and I go to the end is in b, that is exactly the condition I need to be inside of the preimage of b. So that all by itself tells me that that x is in the preimage of b. So that one's not very hard. And that finishes A. So now we need the proof of B. So let's go and look at B. So now we're looking at if f of x is in f of a. So now we've got a different picture. So we've got, So we've got x here and y there. And we've got an a sitting inside. And then we've got an x sitting inside of that. And then we look at where a goes. So a, say, gets mapped into this thing. So this is f of a. And we look where x goes. So it says, if we take an a, an x here and an a here, we map them over here. So we've got f of x over here. Does that force x to be an a? Well, maybe, maybe not, right? So if I could have, say, x could be out here, and I could have an a here. What if I have two different things that map to the same place over here? It doesn't mean that everything in the preimage has to be there. So for example, let me think of an example. So if I have that cubic again, or a different cubic, if I look at, say, the preimage of whatever this value is, or let's take the preimage of 0. So we've got 1, 2, 3 points that map onto 0, right? So if I have, suppose this is -1, 1, and 2. So if I take A to just be the set 1, 2, and I know that f of A is going to be just 0, then just the set 0, because those guys map to 0. Then I can look, if I let x be -1, then it's true that f of x is equal to f of -1, which is 0, which is certainly contained in fact, it's equal to f of a. But x equals -1 is not contained in a, because I eliminated it. And the point was, I had 3 different values that mapped to 0, and I chose only 2 of them. Okay? What's going to prevent that from happening here is that f is an injective function, so that can't happen. All right? So this was all background. So now we're going to prove that if we have the added piece of information that it's an injective function, then that rules this out. So injectivity rules out this example. Okay, but that doesn't prove our theorem. That's just an example that the hypothesis is necessary in our theorem. Okay, So we're starting with if f of x, so we're going to start with an x in A. So we're given x contained in capital X such that little f of x is in f of A. And all that means is that there exists, how do I get to be an f of A? There exists a little a contained in big A such that f of little a is equal to f of x. All right, that y that f of x gets mapped to. So we could have back here stuck in, so such that whatever y is, that f of x, which is equal to some y, happens to be sitting in the image of A. Okay? So now what we have is a statement that's perfectly set up for invoking the injectivity hypothesis. Because f of A is equal to f of x, what we know is that A must be equal to x by injectivity, which is exactly what we didn't have over in our example over there. Now, since A is equal to x, that tells me that x, which is equal to A, must be sitting inside of A because little a was already in A. And that tells me what? That tells me that, excuse me, x, our original x, was contained in A, which was the hypothesis I was after. So if f of x is contained in f of A and f is injective, then x is in A. Yay. So we've got a bunch of alternate ways now to describe injectivity and surjectivity using the preimage. So a function is injective if and only if for every y in the image, so far that's exactly the same, there exists a unique, exactly the same x in the preimage of y. So that's a new way of saying there's only one thing that maps to y. It's surjective if and only if for everything in the codomain there exists at least one thing in the preimage. And it's injective and surjective if and only if for everything in the codomain there exists a unique thing in the domain that's in the preimage. So this says injective and surjective. Let me get rid of all that highlighting. We have injective and surjective. That says that my preimage, so injective and surjective says that the preimage of any y is just one x. And this is saying that it's surjective if the preimage of y